Good day, everybody. We shall present here our work Scale-Invariant Multi-Oriented Text Detection in Wide Scene Image. This is a joint work by Kinjal Dasgupta, Sudip Das, and myself, Ujjwal Bhattacharya. In this study, we handle multiple challenges in scene text detection, such as occlusions of varying percentages, widely different scales and orientations, degraded image quality, etc. So this is an example of scene image where abundant texts are available, plenty of text embedded in natural scene image, and text spotting helps understanding such natural scenes. Detection of text is required prior to its recognition. But what are the sources of difficulty of detection such text? These include variations in shape, size or scale, orientations, difficult illumination effect, blur, complex background, various percentages of occlusions, perspective distortions, etc. Here are some examples of scene text, and it can be seen how difficult and how various distortions occurs in such text. So what are the existing approaches of scene text detection? In fact, scene text reading systems employ a detection module as the first step. Recently, scene text detection studies have achieved great success. One of the reasons is the robust reading challenge organized by ICIITA 2019. However, it needs more study to obtain a robust generalized system for incidental text. Text detection has been approached as object detection applied to text. They could not be very successful because bounding boxes of such text have different nature than those of general objects. The state-of-the-art object detectors like FAST or FASTER or mask RCNN, even single sub detector, etc., cannot perform robustly of producing such boxes for text. So these often fail to perform on multi-scale, multi-orientation text. Moreover, often these are prohibitively slow. So let us summarize the challenges. Extremely wide variation in text size, shape, scale, and length, possibility of difficult illumination conditions, occlusions of varying percentages, different orientations, different types of blur, complex background, and finally, existence of insufficient training samples of various situations. So under the present scenario, to the best of our knowledge, no single study considered all of the above challenges in the same framework. And some of the few existing state-of-the-art studies include fully convolutional neural network architecture is to detect incidental text, which has been presented in CVPR 2017, combination of low-level and high-level feature maps called FORS, detecting incidental text published in CVPR 2018, FASTER RCNN together with an RNN for detection of syntax of arbitrary shapes presented in CVPR 2019. Also, mask RCNN has been used for detection of syntax of arbitrary shapes, which has been presented in ICIP 2019. Here we can see the architecture of East published in CVPR 2017, and on this right side we can see some of the outputs of this East framework. Next we can see on the top of this slide the architecture of FORS published in CVPR 2018. This uses a shared convolution architecture shared between the text detector and text recognition branch, and the shared convolution architecture can be seen the details in the bottom of this slide. And next, flowchart of adaptive text region representation method. This uses a text RPN which generates text proposals of input image, and RNN-based refinement network uses CNN-based feature maps of the input image to verify and refine through the text proposals. And some of the outputs is shown in the bottom of this slide. And end-to-end text spotter by Quinn et al. Uses detector, which is basically a mask RCNN. Mask RCNN outputs a regular bounding box and its instant segmentation mask. For each text region, a minimum area rotated rectangle or a general polygon is fitted to each mask for respectively straight or curved text region. So now let us summarize the shortcomings of existing SOTA models. These include to handle text with difficulties in training the network to handle text with perspective dispersions, to handle partially occluded text, to handle non-uniformly illuminated text, to handle blurred text, to handle text of widely varying scales. So what is our contribution? Proposed syntax detector trained suitably to handle text under widely varying scales and orientations, occlusions of varying percentages, severe degradation in the image quality, etc. Proposed system is based on a deep architecture which includes a novel feature representation block called FRB. Proposed FRB performs efficient abstraction of input information at multiple levels. This FRB consists of multiple Gabor convolutional layers arranged in multiple rows and a multi-scale feature refinement model called MFRM. Here we are showing the proposed deep architecture, and the initial block of this converts an input image into 4 orientation channels, as can be seen from here. Next, we use a Resonate 18 based feature extraction block modulated by Gabor orientation filter. The output of the last layer of backbone Resonate 18 is passed to a block consisting of multiple Gabor convolutional layers arranged in multiple rows, followed by a multi-scale feature refinement model. This is a novel introduction of the present study. The objective is to increase the robustness of resulting features against various distortions such as scale change, rotation, etc. Feature maps computed at a higher layer, such as first and second rows of this FRB, before entering into the Gabor convolution layers of the next lower layer, second and third rows respectively. We also considered kernels of different sizes in the 3 rows of the FRB to tackle the enormous differences in the scales of syntax. The larger kernels capture information in the global sense, and as the size of kernel gets reduced more and more, local information gets captured. So next, the MFRM. The objective of using the MFRM is to make the learned features sufficiently abstract. This MFRM consists of a 4D IRNN module, a traditional convolutional layer, and attention map and aggregation layer. 4D IRN module extracts the contextual features, and it consists of 4 number of RNNs, each of which is fed with a sequence of n by 4 channels of the input feature map of these 4 RNNs moves over its input channels in 4 distinct orientations: left to right, right to left, top to bottom, and bottom to top, such that they produce different contextual features from the respective sequence of n by 4 input channels. Next, these 4 sets of contextual features are simply concatenated to produce its contribution towards the input of the aggregation layer. So this is the aggregation block. So the CRFs of this aggregation block refines its 3 input features and produces aggregated feature. 3 input features comes from 4D attention map and the last convolution layer of the bottommost row of the Gabor block of the FRB. So next is the deconvolution block. The output from the aggregation layer is passed to the next deconvolutional block. It consists of 4 decon 3 cross 3 operations. These 4 decon 3 cross 3 operations produce feature maps of 256, 128, 64, and 32 channels respectively. In the process, intermediate feature maps of FRB are added to the first output of the first and second decon 3 cross 3 operation. So the next is the detection branch. This is similar to the detection branch of each network. It consists of 4 convolution operations providing, these are the 4 convolution operations providing score map, 2 R-box geometries, and 1 quad geometry. So Some of the details of training of this network, this includes various strategies such as mask and predict strategy. In this strategy, we first randomly mask certain text regions of the scene images by black patches of different sizes and then ask the network to predict text regions irrespective of it has been masked or not. So in the bottom of this slide, we can see at the left the original image, and on the right we can see that a part of the text has been masked by black region and ask the network to be trained. So similarly, we consider pixel-wise blurring. In this approach, we apply a certain percentage of pixel-wise blurring in the input image for training with samples affected by deformation of varying degrees. So in the bottom of the slide, we show on the right if such a blurred image where 30% Gaussian blur has been applied. Also, we consider curriculum learning. Curriculum learning is a way of training a machine learning model where more difficult aspects of a problem are gradually introduced in such a way that the model is always optimally challenged. In this work, we employed curriculum learning with respect to progressively developed pixel-wise blurring, masking percentage, and complexity of images to allow the feature learning invariant to image regression, occlusion, and image complexities. So here we see some examples of these various difficulties posed to the training time to the network, and on the top right side we see two such random masking applied. On the bottom to the left 30% Gaussian blur applied, and on the bottom right we show that both pixel-wise blurring and masking is applied to the network. And we also simulated this proposed framework on 4 benchmark datasets, which include ICDA 2015, ICDA 2017, MSRATD 500, and COCO text databases. We have trained our Gabor convolution layers with 4 orientation channels and set the scale at 4. The proposed architecture is trained using momentum optimizer with an initial learning rate of 0.01 and momentum of 0.9. We made use of random mirroring, resizing, and variations in brightness and contrast to each sample for purpose of data augmentation. And the data sets we use the details, training, validation, and test sets are shown here. And on the right, we have shown pie chart to show that the training samples mostly composed of COCO text data, and while the text samples mostly composed of ICDA 2017 data and COCO text data. And here we show the comparative detection results of the proposed framework. Our results of our framework is shown in the bottom layer, and it can be seen that with respect to the 2015 database, our framework provided best results in respect of recall and S-score, whereas for ICDA 2017, our proposed method provided best result with respect to all the 3 measures. And when we considered MSRATD 500, our framework provided best result with respect to precision and F-score. And in case of COCO text, our provided best result with respect to both all the 3 measures, and the second base is highly lower results than our. And here we show some examples of difficult text detected by the proposed method. And finally, we will conclude. We introduced a novel FRB in a deep architecture. FRB leads to efficient abstraction of the input information. Curriculum learning with respect to the blurring and the complexity of the image sample has helped us. We use the mask and predict strategy to enable the network to produce satisfactory results in cases of partial occlusions. We conducted extensive simulations on 4 benchmark data sets. Simulation results have been compared with the existing SOTA performances. Proposed framework efficiently takes incidental text independent of its language. It can take care of uneven lighting condition, blurring, partial occlusions, and scale variations. Thank you for attending my talk.